Okay. So here is the homework talk video for Module 6, Homework Booklet 2 on Quantitative Basics. Okay. So let's get into multiple choices. With this booklet, there are 20 multiple choices and a few extra extended responses. And this booklet is quite long. It's supposed to be like a homework for 2 lessons. So it's a bit longer than the usual homeworks. So we'll go through it together. So question 1 says, what is the pH of a solution that has a concentration of hydrogen ion of 4.5 10 to the power of negative 5 moles per liter? Use definition of pH, okay? So pretty straightforward. So pH is equal to negative log base 10 concentration of H plus, and just substitute it in and you will get your answer. Uh, all of the answers here um, are correct. You just have to pick the correct decimal places, right? Remember that for pH calculation, we need to leave our final answer in terms of like the equivalent suffix. So in this case, it will be 2 significant figures for the linear scale, and then that transfer into pH scale in terms of 2 decimal places. So the answer is 4.35. Question 2, the concentration of hydroxide ion in a solution is determined to be 1.2 times 10 to the power negative 4 moles per liter at 298 Kelvin. The pH of this solution is, okay, so this one you use the definition for self-ionization of water. Equilibrium constant Kw is equals to Ka times by Kb is equals to Kw. And we know at 25 degrees Celsius, this is exactly 10 to the power of negative 14, given on the formula sheet, all right? And then, okay, so yeah, so this is also by definition equals to H3O plus and then OH minus, right? You don't actually need to use this part for this question. It's given that hydroxide has this concentration, right? And then you can rearrange for hydronium ion. After you rearrange for the hydronium ion, put it in the pH definition, okay? To get the final pH. Okay, pretty straightforward. Question 3, 15 mils of a solution which has a pH of 3, is diluted with 450 mils of deionized water. What is the final pH of the solution? Right, so you want to work out the initial concentration of hydronium from this pH, yeah, and then find the moles by multiply by the original volume, and then divided by the total volume. So this added to that, right? That's the new concentration for hydronium. And then plug it into the pH definition to get your new result. Question 4. 10 mils of a solution which has a pH of 5.7 diluted with ionized water, so that pH goes to 6. What volume was involved? So pH tells you the concentration of hydronium, and then yeah, and there's a change of pH, so there's a change in concentration, and then just rearrange your equation. You should be able to work out your volumes initially and finally. Okay. Question 5. So what is the mass of sodium hydroxide that's required to be added into 15 mils of water so that you achieve a final pH of this? So from the pH, work out the concentration for hydroxide, right? You can do that. You can do that pretty easily with the pH and pOH conservation, right? So pH plus pOH is equals to 14, right? So knowing pH, you know pOH, knowing pOH, you know OH concentration. And then when that's obtained, right, this is a strong base. So the concentration of that is the concentration of sodium hydroxide multiplied by the molar mass to uh, and then multiplied by the volume to get the grams, okay? Question 6, the equilibrium constant Kw for the self-ionization of water is this at 40 degrees Celsius. Okay, this is different compared to 10 to the power 14, which is the value at 25 degrees Celsius. And just be aware of this. That's the equation right here. What is the pH of water? So we know that water is neutral, so that means there is equal concentration for hydronium hydroxide, and then you want to take square root of this, and that will be your concentration. Of hydronium and then put it into the pH calculation, okay? Or it's you can use the conservation relationship where pH plus pOH in general is equals to pKw, right, as we go through in class. You can calculate pKw using this value by putting into negative log base 10. And yeah, because since they are the same, it's pretty much just 2 times pH. So it's just pH is equals to pKw divided by 2. Okay. And there's many different ways you can do this. You can calculate the concentration for hydronium explicitly, or you can use conservation laws. Question 7, 0.02 moles per liter of acetic acid has a pH of 3.22 percentage. What is the percentage of acetic acid ionization in this solution? So calculating percentage ionization, given that the pH is 3.22, this tells you the concentration for hydronium ion at equilibrium. And the value of that divided by this should be giving you a fraction of how much is ionized. Yeah, you end up with D as your solution. And question 8, a table shows the approximate pH of some common household items. So you have laundry detergents, lemon juice, milk, and baking soda solution. Which statement is correct? So the right answer is B, in which case it says that the concentration of H plus in milk is 1,000 times greater than baking soda. All right, so remember that pH scale is a logarithmic scale on base 10, right? So baking soda is 9, while milk is 6. So there's a difference of 3 units of pH. That means it's 10 to the power of 3 amount of difference, right? So it will be 1,000 times. Milk obviously is more acidic, so it has more acid. Yeah, this is why we choose B instead of D. Okay. Question 9, what is the pH of the resultant solution after you mix this much amount of nitric acid with this much amount of sodium hydroxide? So this is exactly one of the type of non-equilibrium sort of acid-base reaction that we talked in class. Right, so there's a neutralization. Yeah, work out the limiting reagent, find out how much is left. All right, after all that calculation, you should get D. If you are still struggling with how to calculate this, let me know and we'll go through in class. Question 10, we consider the following equilibrium, ammonia and fluoride, right? Consider this as a neutralization, has an equilibrium constant of 8.4, 10 to the power of negative 21. Very unlikely. Which row of the table correctly identifies the strong acid and strong base in this system? Yeah, as like this reaction, right? That's an acid, that's a base by definition. Yeah, but this equilibrium constant is very small, meaning that at equilibrium, the position of this equilibrium is pretty much like directly reverse, right? At the point that we just assume it sort of goes all the way, okay, to the left. In that case, we want to say that the strongest acid, right, will be HF right here, and then the strongest base is the ammonia right here. Okay. Yeah, because in this reaction, there's multiple acids and bases. It's 2 acids and 2 bases. You know, we want to select the strongest one, which is the one that forces the reaction go to the left, according to equilibrium constant right here. So use the following information to answer 11 and 13, up to 13. Okay, so strength of an acid can be described by pKa, or the degree of ionization. Yeah, sure. A 0.3 moles per liter propanoic acid solution has a pH of 2.7. What is the pKa of propanoic acid? So for this question, from the pH value, you know the concentration for hydronium at equilibrium. Formulating an ICE table of propanoic acid, knowing that it's a monoprotic acid, right? You can work out the pKa value. You can work out the Ka value and then put negative log on it, so it's pretty straightforward. Question 12 is that work out the concentration of hydronium as the same way as we did for question 11. And after that, we make the division with the initial concentration of 0.3 and then put it into percentage, and this is what we got for question 12. Question 13. Which of the following role of table correctly identifies the effect of diluting a solution of acid on its pKa, pKa value, and then the degree of saturation? Remember that Ka, or equilibrium constant in general, is only a factor of temperature. Nothing else is okay, is able to change K value. So dilution does not vary your K value at all. Hence, your pKa value does not change. So it's either C or D. Well, degree of ionization does increase because, like, remember that we have two aqueous product, right? So HA plus water goes into A minus and H0 plus. These are aqueous, so there are two aqueous reagents, while there's only one aqueous reagent at the left. So the effect of dilution is more significant to the product. All right, so you want to shift forward to increase the more dilution effect. That's causing the product to decrease the concentration. So the degree of ionization actually increases, okay? Because you ionize more by shifting forward. Question 14, when sodium acetate is added to water, remember that sodium acetate is the conjugate base for for acetic acid, right? It's a weak base. So there you go, Kb that. Which of the following roles of the table correctly identifies pKa of the acetic acid itself? So remember that between conjugate pairs, in this case, acetic acid and acetate ion, they have a pKa and pKb conservation relationship, in which case pKa plus pKb is 14, or at 25 degrees Celsius, or Ka times Kb is Kw. Okay, so you can work out your pKa from the conservation relationship, right? It would be A, and they're conjugates, so it will be a conjugate acid. Right, so question 15, the pH of 0.1 moles per liter of this acid, right? What is it called? I actually don't know. I have to look this up. Okay. So pKa is 1.96 and 0.1 mole per liter of that were measured. Is this a typo? I think it's a typo because it's supposed to be an O2 here as well. Uh, oh, I mean, oh yeah, this is a different acid. Okay, yeah, sure. Different pKs. Okay, so they are measured. The pH of they are measured. All right. Okay, which solution has a lower pH and why? So the same concentration, right? And then looking at the pKa value, this acid is more sort of dissociable, as in its pKa value is smaller, which means the K value is larger. So the ion is more equilibrium. Okay. Right. Oh yeah, so chlorous acid. Yeah, there you go. That's the name. And this is hypochlorous. Yeah, and then about something about the chemical mechanism is that the reason that this is more sort of acidic, it's a stronger acid, is because there's two oxygen. Yeah, this extra oxygen gives more electronegativity away from this hydrogen, so that when this molecule loses a proton, and because the oxygen sort of attracts those unstable electron, it sort of preserves it a little bit, so that this molecule after donating is still stable. Okay, it's stabler than this. Okay, because of that oxygen atom. Oh, good. And then question 16 and 17, we have information of sulfuric acid, right, has two protons that you can donate. So that which corresponding to two donation, which corresponding to two Ka, which corresponding to two pKa values. So correspondingly, they are -3 and 1.92. Question 16, which of the following correctly shows the conjugate base for that? Remember that conjugate pairs must only be differed by one proton, so it will be HSO4 minus. Okay, the pKa value for that will be -3. Uh, so oh yeah, so like right, my bad. So the pKa value for H2SO4 to its conjugate base is -3, but the conjugate base, right, in terms of its pKa value will be 1.92. Okay, so don't get this confused, a different reaction. Question 17 says a solution of sulfuric acid, the pH of 1.92. This concentration of the hydrogen sulfate in the solution. Um, so hydrogen sulfate sulfuric acid has pH of 1.92. So that has the same, like the concentration of it. Yes, it will be equal. Otherwise, like your pH is equal to negative log base 10 of your hydronium ion concentration, right? And your pKa is equal to negative base 10, right? And you have your hydronium ion on the top, and then you have your um, concentration of the other stuff, SO4 minus, and then you have your concentration of the original acid itself. But they have to be, because we have K, pKa and pH being equal, right? 1.92, so they have to be equal, right? So they must be equal so that they can cancel out for this expression to be the same, right? So therefore you can say that this is equal to the concentration of SO4 2 minus. Okay. Question 18 and 19. Phosphoric acid is a weak triprotic acid with 3 pKa values. There you go. Right, so which of the following 0.1 mole per liter solution will have a highest pH? Obviously that, okay, so PO4 minus, 3 minus are able to ionize 3 times by dissociating it with water, okay? Okay, question 19. In a phosphoric acid solution, the concentration of this and that are equal. What is the pH of the final solution? Okay, so knowing this is true, concentration of this and that. So from the pKa value of this one, so you know this reaction, the first ionization, right? Reversible into H3O plus PO4, H2PO4 1 minus, right? They are equal, so your Ka here is simply equals to H3O plus's concentration. They cancel, right? So they're equal. Water is just one. So when you do pKa, that's just P of that, which is just pH. All right. Since they are equal, your pH is equals to pKa, and so your pH is just 2.12. This is like the same logic as we did above for, I don't know, for which one? For question 17. Okay. Right. It has some association to the buffer solution that we're going to do next booklet. But it is what it is. Question 19. In a phosphoric acid solution, the concentration of that and that are equal. Yeah, we've went through this. Question 20, the pKa value for ammonia is that's what is the pH of. So you want to work out, because ammonia and ammonium, oh, sorry, my bad. Wait a sec. Yeah, so ammonia is that, it's a base, right? So you can work out the um, you can work out the concentration of the hydroxide ion when ammonia ionizing water using pKb, right? And then you can use the pH and PaOH conservation relationship to work out the pH. Okay, it's pretty straightforward. Once again, I didn't really show you how to calculate this, right? A lot of the ways to calculate all this is done in class. If you have any question, just let me know. I'll teach you again. Up to extended responses, question 21, so that the students prepares a solution, 0.4 moles per liter of HF. It is measured to have a pH of 1.33. Show that the concentration for that, so pretty much just use the definition of what pH is. Easy, and two significant figures as the final answer. Question B, calculate the percentage ionization. Once again, by definition, this shouldn't be that hard. Question C is now we dilute it with 200 mils of deionized water, and then we take half of it, right? And then we mix with KOH. So it's kind of like dilution, and then part of it goes to neutralize with another thing, and limiting reagent and all that, okay? So first of all, write down the neutralization reaction that is occurring, and then check for which one would be the excess reagent, okay? Using the method that we did in class, okay? So we end up saying that after dilution, it is a different volume, Okay, so yeah, so it's the question asks us to completely neutralize the HF solution. So we just need to match the molar ratios and then right and the equal ratio. So N1 is equals to N2, just equate. And the N2 is just because it's only half of it, so you want to divide it by two, and this is rearranged into this equation, and then you want to rearrange for the volume for HF. So sorry, the volume for KOH in order to neutralize everything. So you end up just solving a solution, an equation. Okay. Question 22, we have 2 grams of calcium hydroxide added to this much of hydrochloric acid. Balance chemical equation goes as this. Don't forget to balance it, the pH. So neutralization reaction is occurring, so you want to find out which one is the excess reagents by checking, first of all, writing down the molar relationship, the molar ratio, and then check out which one is limiting reagent. You can do this by testing out which side is larger or smaller. And turns out that HCl is the excess reagent. How much is left? You can calculate that by denoting the how much is left by N2 final. It is equals to the initial amount minus how much that's changed during the reaction. But the initial amount is just what's provided, and C times V, right? What's provided and minus what's reacted. So what's reacted is just equals to the mole of the limiting reagent times by 2, according to the molar ratio. So yeah, put that together, you can work out the concentration for H3O plus. Since we have HCl as a strong acid, it's just equal to it, okay? And then the final number mole divided by volume gives you the concentration. Be careful that this volume is the volume for the final solution, which is V2 by itself. And then just work out your pH by definition. 2 decimal places as we use the uh, wait, it shouldn't be 2 decimal places, it should be 3 decimal places. Yep. But like, yeah, let me change that. So I don't know exactly what this is, but this should be 3 decimal place. Okay, just be aware of that. Yeah, it should be 3 decimal because these are all like 3 significant figures, and then yeah. All right. So question 23. Sodium barium, solid barium hydroxide added to, again, a neutralization reaction. You do this question very similarly with the previous question. Okay, this case you have like to calculate the molar mass and all that, but it's ideologically identical. Okay, so right, just this is the sample answer. If you have any question, let me know. I won't go through this question is pretty much just practice how to do this type of neutralization with strong acid and strong base. Something left over, calculate the pH due to it. Pretty easy. Question 24, many bases sparingly soluble in water. By a little bit of equilibrium involvement. So we have a saturated solution of strontium hydroxide. It has a pH of 11.73. You can calculate the KSP value for strontium hydroxide. Just because you know the pH, therefore you know the hydroxide concentration, right? At this point, if you don't know how to do that, let me know or look at the booklet. It's pretty easy using the conservation laws. Right. So there. So work out that, and then it's half of it. So work out that as well, and then plug it into the KSP definition. You will get your answer. 4 sig figs, as we have. Yes, this should be 2 sig figs. So yeah. Um, this is really a typo. It's 2 sig figs. We only have 2 decimal places for pH. I don't know what I'm doing. Okay, so I'm gonna change that. Sorry about that. Okay, and question B, what mass of sodium hydroxide need to be added to 50 mils of water to have the same pH? Okay, we want to have that, the hydroxide is equal to that. Therefore, if you can rearrange for the concentration for strontium hydroxide, it will be half of this, okay, because the molar ratio for hydroxide, and then just the mass will be whatever it's required, okay? Right. Question 25. So the graph shows this is HEC question. As you can see how the graph is an HEC style. Right? Whenever you see those graphs like written in a different font, sort of like this Times New Roman, you can expect this is HEC. Okay, this question is very I like this question. So the question says the graph that shows the pH of various concentration, it's a logarithmic scale. Okay, the scale is logarithmic, but it's expressed in terms of linear scale, but it's still like, the space separation is like tenfolds different. So this is in fact logarithmic. Okay. Yeah, so we have different, we have a weak acid, you should know that. We have a strong acid right here. And then their pH in relation to the concentration in tenfolds difference. Okay, right, we can see how for HCl we have a linear line. And then for HF, we still like, we probably have a linear line, but not that much. Look, we'll see. So the analysis, the question A says to calculate the degree of ionization of 0.01 HF. That's just picking a point. So that's just a point here, and then use that point. You know the pH, which you know the hydroxide, sorry, the amount, sorry, the hydronium ion concentration at equilibrium. Use definition to work out a percentage ionization. Question B says to explain the trend. So a real band 6 student should be able to explain the trend while also quantifying it. Maybe try to give like a relationship that demonstrates the relationship of the lines. Okay. Right. So the graph depicts a systematic reduction in pH, right? So both decreases in pH, right? As we expected for acid. The more concentrated you are, you dissociate more, so the less in pH. Uh, so for hydrochloric acid, which is a strong acid, right? So you write this equilibrium, and you write without the equilibrium error, okay? So the pH is exactly equal to that. So we get this relationship. pH is proportional to the tenfold difference of the concentration. It is -1 as your gradient, right? Which is exactly what we get here, right? It's just a straight line going downward. So satisfies the linear relationship which with the -1 gradient in the graph. On the other hand, we have a weak acid, which does not ionize completely and forms equilibrium instead, with a small change at equilibrium assumption, right? We can say that how the hydronium ion concentration is like literally just roughly equal to that, right? We take a small change. So that's HF, right? After ionization, it's still sort of just HF, right? And then you end up getting that. You can verify this with IC table if you want. So if I plug this into the pH definition, we get that, right? So, and then use the log rules, right? The square root becomes a half in front, and then we can separate the multiplication. Okay, and then use definition of pKa, right? We end up getting this. And then we're plotting against the pH and that. Okay, so this is our independent variable. This is the dependent variable. Do you see how this is another sort of straight line, but with an intercept, right? So it's like a sort of shift upward, and then the gradient is no longer -1. And this is why we have a less steep slope, right? Because -1, right? It's more steep than -half. And then it's above it. It's above the HCl is because we have an extra term. Plus a half of the pKa. So because of the weak acid property of HF, it's weaker so that the pH is systematically higher, right? Higher by half of pKa value. Okay. So yeah, this explains the trend. You can theoretically derive it even. Okay, very nice. Question 26. So excess barium hydroxide was added to 100 ml of water, 25 degrees Celsius. Calculate the pH. Well, yeah, you just because the barium hydroxide is a weak base in terms of this, as a salt does not dissociate completely. It has a KSP on the formula sheet. You can work it out, very easy. Question B, excess barium hydroxide added to that, another neutralization, this time with equilibrium consideration. Okay. So don't forget about the barium that's already been produced after during the neutralization, right? This becomes sort of the common ion effect, right? Okay. And then you assume small change, everything else which is identical to module 5. Okay. If you have any question, please let me know. I'm going to go through this faster. Question 27. We have a bottle of sodium hydroxide. It has a pH of 12.8. Uh, yeah. Okay, so the following method was followed to make the above solution. We weigh out the solid sodium hydroxide in a beaker, and then we add deionized water to dissociate, and then we transfer sodium hydroxide solution to 50 ml, and then we rinse the funnel with deionized water to make sure everything is in the mixture. Add deionized water until the bottom in this case, so that regulates the concentration, and then make sure everything is dissolved by flipping the solution. Okay, calculates the mass of sodium hydroxide that's required to achieve the pH as shown. So we know the hydroxide concentration, right? Can be worked out from the pH, just 14 minus pH to get the pOH, and the negative of that, 10 to the power of it. So that's the concentration and divided by V, right? So it's equals to the mass divided by molar mass divided by V. Just rearrange for the mass, okay? And that's our final answer. B, justify a reason for step 4, right? You want to make sure because liquid is split everywhere on the surface of the glass. You want to rinse it off to make sure every single sort of everything is dissolved into the mixture instead of left over on the glass due to the surface tension of water. Okay. Question 27, what volume of this much is required to the above solution to change the pH into 3? So pH equals to 3 gives you a concentration for hydronium ion. Okay, you want to first of all completely neutralize the base, and then you want to what's left to produce the pH of this. Okay, so after the reaction between sodium hydroxide, right, you get that. So for which your total HCl number of moles is equals to concentration times by volume, right? We know the concentration, we need to know the volume, so we want to find the V0. So what happens is that this equals to whatever that's left at my final H0 plus, which produces pH equals to 3, right? Well, that's just what this is, yeah? And then we're calculating in terms of number of moles, so we have to multiply this by the total volume at the end, which is the original concentration for sodium hydroxide at V0, plus uh, on the volume that we added in V0 plus the volume for sodium hydroxide. That's the final concentration. That's the whatever is left. So added on top of whatever that's being reacted. So what's being reacted is equal to the concentration of sodium hydroxide times by its volume. That's the molar ratio is 1 to 1. And then you can substitute values into this big equation to get your final results for volume. Okay, 1.5 liters is the final answer. Question 28. Hydrocyanic acid, HCN, is an acid with an acid dissociation constant of this much. Assume the temperature for this question is constant at 25 degrees Celsius. Show that the base dissociation constant for the conjugate base, right, is this much. You can use the identity. It's very straightforward. Calculate the pH, potassium cyanide. Okay, so potassium cyanide dissociates completely, but cyanide ion from the potassium cyanide dissociates partially. So you want to consider that using Kb, work out the concentration for hydroxide and reverse engineer it into your pH using conservation laws. It's pretty straightforward. Question 29, two different beakers, acid X and acid Y. Okay, compare the concentration and strength. So concentration can be straight away calculated from the pH and so the percentage ionization, right? You can work it out. It's pretty straightforward. Okay, so the percentage ionization is equal to the concentration for hydronium, yeah, which is 10 to the power of the negative pH, right, divided by the original uh, uh, concentration, and then rearrange for that, you get the original concentration. So you can compare the concentration. In this case, HY, acid Y would be larger than acid X. And in terms of strength, you just look directly at the pKa value. And the smaller it is, the stronger it is. So acid Y is stronger. Yeah, pretty self-explanatory question. Question B is the one that's kind of challenging and then sort of like like it's just logically difficult. Okay, and for me, I was like thinking about this question for a while. Okay, yeah. So for this question, the question says that the a different acid is added to Y, so the pH decreases due to excess hydronium ion coming from other source. So in this case, that because like for a single acid, right, whatever H2O plus it produces is going to equal to whatever conjugate base it produced from the ionization. However, in this case, the H2O plus come from something else, right? So your conjugate base is no longer necessarily equal to it. How do I calculate the concentration for the conjugate base, right? If it's not equal. So the fact that we just need to treat this as a like some sort of common ion, but it's not really. So the idea is that we start by talking about the initial concentration of HY. So we know that it's 12% ionization. Okay, and then we know the final. Yeah, the final is just that. So the initial is just this divided by the 0.12, 0.12. Okay, and then we say that how much of the different acid editing is unknown that produces unknown amount of this. Okay, and then we say that, and then this also partially ionized by X amount. Okay, so you end up getting 0 to X into this X, and then this minus X to this X. All right, but we know the final concentration for hydronium ion has to be this, and then from this equation, equate with your Ka, which you can get from the 10 to the power of negative pKa, and then you can solve for X using this linear relationship. And that's the final answer. It's a bit challenging because people try to figure out how, like, they think the initial concentration for that is 0. It's not. There's some amount of H2O plus came from that different acid, which makes this and that not to be equal. Okay, but specifically how much doesn't really matter. We don't really care because we know that at the end of the day, the pH is 1.73. We already know the concentration for hydronium at equilibrium. So yeah. And then question 13. Sorry, 30, amphiprotic acid. So this is a bicarbonate ion. It can act as an acid or a base, right? Given the K2 value for both reactions. And then A says to what property of hydrogen carbonate does these two equations demonstrate? The amphiprotic property of bicarbonate ion. Okay. So use the information above, explain why sodium bicarbonate ion has a pH that's above 7. So it's a basic pH, although it still acts as acidic. This is because that the K value for when it acts as a base is larger. Okay. So yeah, at equilibrium, it's more like producing more hydroxide ion than hydronium ion, so it's basic. So question 30 is just a calculation. Use your Kb value, it's pretty standard, okay? And work out the concentration from your mass and IC table. Yeah, this one, it's just very standard. A very standard weak-based dissociation calculating pH question, okay? And then 31, this question is giving you ammonia and then it acts as an acid, but this reaction is like K is that small. So a saturated solution of ammonium chloride has a pH of 4.2, calculate the KSP. So you know the pH, that means you know the hydronium ion concentration at equilibrium, okay? Which is going to be equals to, because like that is going to equal to that because the molar ratio. So if they're equal, and then Ka is like this times that divided by that, but they are equal, so that's just 10 to the power of negative pH squared divided by whatever this is, and then rearrange for that. Okay, so this is at equilibrium, but whatever this is at equilibrium must came from the dissolution of ammonium chloride. Okay, so again, KSP is equals to ammonium times by the chloride in its concentration. Okay, but molar ratio are the same, so chloride is equal to that. But that has to be equal to this for this pH to be 4.2. Okay, so you end up just squaring this number. K, you already know, just rearrange. Okay. Yes, this one is because we're doing everything in reverse. It's a bit logically challenging. Yeah, but it's quite common. HSC question is really fun. Like they like to ask questions that go in reverse than most of the questions. Okay, you have to be very familiar with how to do this. You may use ICE table for this. I don't know. Like for me, I feel like it's not gonna help a lot. Question 32. You're given a weak acid and then its conjugate base, right? It's called a benzoic acid. If you do organic chemistry, you can draw its molecular structure. So this is benzene. You get that. Okay, and this hydrogen is donatable. So that acid has a pH of this as at 0.1 moles per liter, and the conjugate base has a pOH of that, right, moles per liter, at 0.1 moles per liter. I want you at this some temperature of 50 degrees. The question want you to work out the Kw, all right? So at the first instance, this question looks pretty scary. Like, how am I supposed to get Kw Simpson related? But if you recall the definition of what does it mean to be neutralized, and then what's the significance of Kw in all this, right? It should be quite straightforward. So notice how like Kw is K times Kb at the same temperature for conjugate pairs, and then you can calculate the Ka value pH that's given for the benzoic acid, right? pH given for benzoic acid equilibrium tells you the equilibrium concentration for hydronium ion, which is the same as that. You can work out the Ka value from it. And then likewise with the conjugate base has a pH of that, tells you the concentration of the hydroxide ion, which gives you the Kb value for that. Likewise, just do IC table. And then multiply them together to get your Kw value. Okay. So 5.1 times 10 to the power of negative 14, 2 seconds. Okay, and that will be it. Okay. This booklet is supposed to cover all the sort of calculation basics, calculation fundamentals for like this module. In the future, we're just going to apply them, okay, in different chemical concepts. Okay. Right. So that's it for this booklet. Enjoy chemistry. I'll see you next week.